So those of you who were fortunate enough to hear the presentation by Holger Hors yesterday will be aware that the biggest danger of AI facing us is not the development of Skynet and monster robots that kill us all, but the use of what we could perhaps call crappy AI made in a crappy way and used in a crappy way. And one of the major problems, one of the major things that causes an AI to be not great is using it in an indiscriminate way. You have a problem, you throw some deep learning at it, and now you have something that can make a decision. And the decision is not being questioned anymore. The algorithm says, do this, and so the business, the government, whatever, your media selection no longer is being critical about what are the reasons for making this decision. And so the core concept underlying this is the explainability of the system. We need to have AI where we can understand why it has made the decisions that it has made, so we can see, well, is this a good decision, or has it learned something that enabled it to do well on the training data, but that is now making it make wrong or discriminatory decisions. So it's very important that we learn to understand what are our AI systems using to make the decisions that that are underlying so much of our society now. To explain some of this to us is Barbara Hammer from the University of Bielefeld. Sorry, I moved away from my notes too early. And the subject of her talk is explaining neural networks deep and shallow. Please, I very much look forward to this.
Thank you very much. So Bielefeld doesn't exist, so you just mirrored the myth about that. So please let me start with the motivation why we need to explain neural networks, or more generally AI principles, apart from that it's a law with the AI Act being just ratified. So let me start with my favorite AI failure. So there are every year top 10 AI failures, and this is from time of COVID, where in a Scottish soccer club, a intelligent camera was supposed to zoom on the ball. I don't play 90 minutes of the soccer game, but just a few spots. And please see whether you can spot the ball the camera is supposed to zoom on. This was going rockets. And it's a bit erratic. So the problem is actually the camera was not seeing just one ball, but two. One, the real one. The other is the bald head of the referee, which just looks so much more like a ball as compared to the original one. And this is very typical once AI is delivered to the market. So there are more failures. Yesterday we heard from Christian, for example, that there are biases. And this is an example where the bias was published from Boluk-Basi, man is to computer programmer as woman is to homemaker, which refers to the equivariance you want to achieve by embedding text into a vector space. And if you add tokens there, then the problem is that the semantic might be changed. You have technical errors. So in the middle, you see a self-driving car which overlooked a big red fire truck standing directly in front of it. No one was harmed. And it's very nice that the fire truck was also with a 42 on it. And it was just an outlier. And just on the weekend, I started to play around with GPT-4o, trying to have some hallucinations, which gets more and more problematic. German has this wonderful way of having compound words. For example, Rhabarber, Barbara, Bar, Bier. I could this could go on, like Rhabarber, Barbara, Barbier, Barbaren, Bad, Barbier, which makes perfect sense. And this, what is said here, means we have the beer from the bar owned by Barbara, who's called Barbara because she has so wonderful rhubarb pie. And if I ask ChatGPT, so please tell me who owns the bar and what is a person doing in the bar, then the problem is that GPT is doing a wrong tokenization because you have this barbier or bar beer, so beer of a bar or the barber, and this tokenization is wrong, so meaning this is a person for GPT who owns a bar and is shaving in the bar, which might be illegal in Germany, so it's a complete mess, although it looks pretty good. The problem is probably not so much that all AI makes errors, but these are very unexpected and not aligned to what humans would do. And so they might have a very negative impact on individual persons as well as society. And therefore, there is a need for having alignment, and one way to get to an alignment is to enrich machine learning models, which are black box models, by ways such that humans can more easily understand those. And I would like to start with like a very short overview about XAI methods existing, which is probably the shortest existing overview. And then I would like to go into 3 examples of XAI. One is an application for XAI methods in the water distribution domain. Another is how to have XAI methods if we do incremental learning. We have just learned this year that online learning is important. Yesterday we had a very wonderful talk about incremental learning. And how can we judge synergies? So if we have not 1, but 2 or more people, so a team, which is the SHAP IQ. So let me start with a very short overview. What do machine learning people mostly understand under this umbrella of XAI at the moment? And if you delve into that, it might be a bit disappointing because what machine learning people currently develop as XAI is very simple. So it's pretty shallow yet. More or less, it refers to every way to equip a function which is somehow implemented by an AI, which might be a classification, which might be a regression. It might also be something estimating a probability for some event to happen. It might be a reject option. So it might be any function with any output which is in some way implemented by any AI method. And you want to equip that with something which is understandable by humans. Often, and at the moment, this refers to static. So meaning it's not interactive and one-shot settings, which is so far a limitation. And having said that, there are some axes which allow you to categorize which methods are around, because there are quite a lot, so close to 100 XAI methods around. You can distinguish why do we want to explain? What do we want to explain? How do we explain, as refers to the modality we use to explain something, as well as how to explain, as concerns how do we compute the explanation. So why? It might be that I want to explain because my system is wrong and I want to improve it, which would be that one. So it's explaining for ML designers. It might be that I want to sell my product and no one buys it if people don't trust it. So you might need a lawn mower who's talking to you. Oh, I will go over this place because it's not yet, whatever. So, and GPT is pretty good at making people trust, although they are probably, GPT is yet crap. Explain to justify, so going for the GDPR or also the AI Act, you might need to have an explanation to fulfill regulatory requirements. And what is probably the most noble intention, you want to explain to discover. So if you have, for example, a medical application, you might want to know what is causing a disease, and then you might want to go for XAI methods which are actually causal. What? There's a big distinction between what is called local and global explanations. So global explanations on the right part would look for your function you want to explain. and try to substitute those by one big thing which is understandable. So probably telling, okay, for each and every input, this is the most important part to look at in the lower right part, because this is the name of the painter, and the costs of a painting depends on the name, nothing else. So that would be, for example, one global explanation for something which has been trained. A local one would look for an explanation which applies to a very specific instance. For example, if you classify this image as this is a husky, then you might say, okay, this is a husky because here on the lower right part there's snow. For another image, you might look at another part. For deep learning, many explanations are local for the simple reason that there is some reason why I used a deep network in the first place, because there is no simple logical formula to describe this thing. Whereas if you go for local things, locally each and every smooth function is approximatable by a linear one, so locally you might have an explanation which is sufficiently well. And then there are many methods on both parts. How to explain? So what is the language I use to reveal what the thing is doing to a human? You might go feature-based. If you have an image, a feature would be a single pixel, and you might highlight, for example, the pixels which are responsible for this being classified as, in this case, a Labrador. This is from the Lime paper, so here you see, okay, if I highlight these pixels, I see, okay, it's a Labrador. It's not the guitar which is responsible for that, but this being looking like a piece of a dog. There might be prototype-based explanations where you refer to this being a medium-sized car because it looks very much like this image where I know it's a medium-sized car in one or the other distance. Natural language or logic. Yesterday we have heard a very beautiful talk about having logic circuits explored. So you might have, for example, visual question answering where you give, in addition to an image, an argument in natural language. Like, okay, this is not a zoo because the zebras are standing in a green field. And you might also resort to visualizations. For example, this is the output of what is called Deep View, which is a method to visualize the classification boundaries of deep networks also in high dimensions, where you see where the points used for training are located and where the boundaries are, and the color indicates where you are sure or insecure. And you see easily, okay, which classes are probably overlapping, where you have outliers and stuff like that. Here, this is even an adversarial example, so you can then have a global view. How is it computed? And that is probably the one axis where most machine learning people delve into, because this is easiest to publish papers based on that. So you have either models which are self-explanatory, if you go for neurosymbolic methods, for example, or prototype-based methods, or the CBC, so classification by components architecture. You might have models which are not self-explanatory, so you need a post-hoc explanation, where you have this distinction into whether you do it completely black box, meaning you develop methods which could be put on top of each and every method, no matter whether it's neuromorphic or deep or shallow. Or you use specifics of the method, like, for example, the LRP, the layer-wise relevance propagation, which is tailored towards deep networks to use the gradients and way to compute the gradients efficiently in deep networks. I'm going to delve into these two. Counterfactuals as the very first one, and Shapley values, which have the benefit, these methods apply to arbitrary things. So no matter whether you have a neuromorphic model or a deep network or a random forest, you don't care. And I would like to start with counterfactual explanations and an application of XAI in a domain which is actually critical infrastructure, so water distribution systems. But please allow me to start to define what is a counterfactual explanation. A counterfactual explanation is a post hoc, black box, example-based and local explanation method. Imagine you have a classifier classifying blue versus green, and you want to explain why is this blue, then the explanation would go for the closest possible input such that it would no longer be blue and say, okay, this is blue because if it should be green, it should look like this one. And you can phrase this as an optimization problem. And actually, that's one thing I always observe in nature, because that's the thing when I have birthday and my husband should buy a nice big present for me, and I have these hints. And then I get this present which I didn't want, and I say, oh, what should I do differently to have the present which I wanted? So I'm not sure whether my husband is using a neural network for that, but I'm still working on this counterfactual input, which gives the other result. What is a problem? If you use these counterfactuals in vanilla form, they give super crap results. And you see that in an example from the MNIST dataset. So if I ask, how should I write this, that it's not a 6, but a 3, a plain counterfactual explanation would give this one for a softmax regression model, or this one for decision tree. And you see, OK, but this is not a 3, come on. What does it mean? The problem is counterfactuals in vanilla form have the same formulation as adversarials. So they are not necessarily intuitive examples. And therefore, what one usually does in practice is that one adds additional constraints such that the explanations are also meaningful in the domain where you aim for. One example would be, which is a general one, to have a counterfactual, which is on the other side, but not just at the boundary, but it is a reasonable sample in the sense that it is on manifold, which you could formalize by requiring that the probability of actually having observed an image or an input which is this counterfactual is at least delta. And this would give you reasonable results, for example, for this MNIST again, if you add this reasonability constraint in the sense that the probability distribution should be at least a certain delta, then you would turn this 6 into this one, which would be labeled 3, and which is reasonable on the one hand. On the other hand, the difference of this counterfactual explanation is no longer big for different models. And you can actually prove that it depends on the data under some constraints only. Now, we want to use that as promised in water distribution systems. So water distribution systems look like that. This is L-Town. So these are pipes. Every place here is a place where you can take water from. And these water distribution systems, of course, get more and more pressure with global warming concerning supply of water as well as quality. And therefore, more and more sensors are implemented there. For example, there might be here pressure sensors, which supervise the system. Depending on where you go, for example, Italy, you have pretty much loss of, or medium Europe, you have like loss of more than 10% due to non-revenue water due to leakages. That's one thing. Another thing is it might be that the sensors get disrupted. So you want to have a supervised system which allow you to do fault detection based on these sensor measurements. So far, no water supplier allowed us to put leakages into their system. Therefore, we go with simulation tools. And there's one popular simulation tool, which is the EPANET, which relies on a steady-state physics simulation of the networks. With that, we did the following. So we developed, and that's what everyone more or less is doing, an approach to detect faults based on these sensor values, and this is a two-staged approach. So the first one is building what would called virtual twin sensors. So for this sensor, A twin is built, which is an inference via a model from the other measurements. So you have the observed one, the blue line, and the orange one, which is, because the senders are not independent, the estimation of what that sender value should be based on the others. And if you have such a model with your favorite time series prediction model, you can resort to a residual approach, which tells you as soon as this quality significantly drops, which is a statistical test, you have an alarm, okay, there's something wrong. Sorry, here there might be either a sender fault or a leakage emerging. This works, and we tried it with the network with different types of leakages, different types of sender faults. All but very small leakages are okayish as concerns that you are able to detect those. But the problem is now you have an alarm, like, oh, something is wrong with your network. So either you put people to each and every place, or you tell, look there, and there's a sender fault, replace the sender. There might be a leakage emerging, beware, it might develop to a burst. For that, we used counterfactual explanations, meaning we ask, if we observe this prediction is no longer correct, how should we change the inputs such that this is correct, hoping that this would point us to the location and where the sensor fault or the leakage is emerging, to having something like that. So these are the nodes. And if this is very high, then we would hope that this is actually the location where we should look at for this fault. The problem is this does not work. We need to add a plausibility constraint. And the plausibility constraint in our case is we don't have just one place. We have many places, which I refer to with Fi. And what we do is we look for the counterfactual such that for each and every place, this error which has been observed is corrected, adding slack variables to make it feasible. And this actually works because this allows us to detect, okay, it's this area, because this would allow us to correct everything and not only this one. So this would be what is this ensemble consistent explanation. And we call this a fingerprint, giving it to domain experts. The problem with XAI is always, okay, is it a good explanation? Can domain experts do something if they see this one? We did user studies, still ongoing, very hard. It's really problematic to evaluate XAI. So what we did is we used this XAI methods as a tool in a downstream task for a machine learning model, hoping that if machine learning can better handle these as compared to plain representations, then there's something inside. And what we did is actually we did a downstream task where, based on either the counterfactual or the plain signals from each and every node, we do a sensor fault classification task. So based on this signal, we say, okay, is this a sensor fault with Gaussian noise? Is it a small leakage? Blah, blah, blah. And the thing is, if we tag the whole signals, a machine learning model, so we used a random forest as one of the best classifiers, is not able to really solve the task, whereas if we give this preprocessed one, we are pretty good. If you want to use counterfactuals yourself, this is a link to a toolbox developed by Andre in my group. But let me come to another explanation method, which is feature importance values. And here I would like to go a little bit beyond this static view into a incremental learning and explaining incremental learning. So what are feature importance values? Feature importance values are the following. If you have an input space, n-dimensional, you have a function, you have a data set, so this could be local or global, depending on whether it's the whole input data set or it's just one single input, then you want to find values which tell you what is the relevance of each and every feature. And let me illustrate that using one important example. So when I did my PhD, I asked myself, oh, which papers get accepted at conferences? It's a very important task. And as a machine learning people, I once started on, okay, I just build a data set, characterize my papers, so whether they're about deep learning, content proof, blah, 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 blah. And I'd see whether the paper is accepted or not, and I build a model. This can tell me that my papers will not be accepted. They will not help me to improve the papers. So what I would love to do to have is a feature relevance vector which tells me, okay, better write the paper well, better do the math correct, better be about a relevant topic. ChatGPT doesn't help you. That's my data set. Okay, and then you would see, okay, yeah, if it's well written, blah, blah, blah. So the three most important features, they allow me to identify, okay, this is what I should do. Many of the existing feature relevance methods have the problem that in some cases you have correlations and you might substitute one by another feature, which would probably mask that I have to write the paper well. In this case, yeah, I could also look at whether I love these beautiful printen. Then it's accepted, which would be another possible way. So the question is, how can we find a mathematically well-founded method which allows us to judge the relevance of a feature independent of how many correlations does it have? And there's a solution to that which actually goes back to game theory, and that's the Shapley value. So Shapley got the Nobel Prize for the Shapley values, which are the following concept. Assume you have a group of players, D. So me playing whatever, soccer with some group of other players. Then you have a reward. So sometimes you win, sometimes you lose. And now the question occurs, how much should each and every player get from the reward? And if I would play soccer in a group, it might be the group always wins, but it's certainly not to me. So how would you see that it's always the other players who should get the credit and not me? There is a solution to that, and actually there is a solution which is a unique one, which fulfills these axioms like efficiency, that you the whole money you give to the players should sum to the money you get from the games. You have symmetry, dummy, very important linearity. So you have a game and another one adding up, then it should also be a linear term for the revenues for the single players. If you require these axioms, which are very natural, then the only way to do this is you have to look at each and every subset of players. Look what would be the revenue for this subset as compared to the subset where I is included. You take this difference, and then you have to weight it with these terms summarized over each and every subset. And now you can use this one to tell what is the importance of features, because what you can do is, if you want to know how much is well written contributing to papers being accepted, you have to look at each and every possible subset of other features. So meaning you have to mask some of those, probably you mask those. You do that for each and every possible subset, and then you'd see how much would the output be changed if you add this well written versus you don't add it. And this difference would be the benefit of this well written in this context. And you have to average that over each and every subset with certain factors. This is what is known as a SAGE, so Shapley Additive Global Importance by Covert-Lundberg. So they used features as players. They used as a revenue, in their case, the improvement in loss if you add one thing. And then they have this Shapley average where they add terms over each and every possible subset of features and see how much this differs. There are two problems here. Of course, if you have just a subset of feature, how can you evaluate a neural model or any model if you have a subset of features only? So you go for the other ones for the expectation. And there's another problem that it's super infeasible because you have to sum over subsets of features. If you have many features, that's just exponential. So you wouldn't do that. So meaning that you need approximation methods to get around this big sum, which is an exponential sum. And what one usually does is one goes for sampling, so using Monte Carlo sampling, which can be written as you have a permutation of features. You look the feature up to I in this permutation, whereas without I, and you have this one, and you add over a number of permutations, which is not an exponential, but just a finite number. You can show that this is an faithful estimator of the value with this, whatever that be. Okay. And I want now to use this SAGE for incremental learning. SAGE as one of the few methods which provably can deal with feature correlations. Incremental learning means that I don't have a task at once, but the task is emerging after delivery. So you have an initial model H0. You might observe data in practice. You are allowed to adapt your model according to that. And that's whatever happens if you have anything, any adaptive app on your smartphone, for example, and you want to personalize it. Okay, we used incremental learning just to show you that this is beneficial. We used that, for example, in collaboration with Honda Research Institute for optimization of movement support systems. So these are persons who were wearing an ICNCE suite, so it's a full body suite where you can observe what motion patterns of this person. And the task is here, the final task would be to develop exoskeletons which can support this person in doing whatever this person wants to do. And in order to be able to do that, you want to know what the person is going to do. For example, here at that point, you want to know, okay, this person is going to squat down. Here it's going to squat up with objects, so I better start some support function with my exoskeleton. And the question is now, can we, is it better to pre-program everything or deliver it and let the person interact with this system to improve after delivery, which would be an incremental learning task? And actually, you can show that we did that for different representations, different models. This is an example curve. So if we come with a system which is optimized, averaged over each and every person, the error is much bigger as compared to if you allow personalization, so you allow the system to adapt according to single person. Meaning it makes sense to learn incrementally if you have systems delivered to individual persons. Okay, if you want to do incremental learning, there's this beautiful toolbox from Albert Biffet. If you want to play around with movement data, so there's this data set from Honda Research Institute where you can play around with actually pretty cool movement data from ICNCE suites. But what I'm looking at is explanations. So it might be that if you have a model which is learning according to a data stream, assume the model is a tree, or we use usually random forests. It might be that here you see that the feature which is relevant is another one during this emergence. And then what you would like to know is, in each and every point in time, what is the relevance for each and every feature? So mathematically, that would be incremental feature importance determination, meaning for each and every point in time t, we want a vector h1t to hnt telling us the relevance of feature I at time point t for the current model. And this might change over time. How can we do that? So yeah, it's a little bit like what we had before. So let's come back to this example of which papers are relevant for conferences. It's now the case that you don't have all the conferences at once, but you have NeurIPS, your papers and the result, then a little bit later you get the ICML results, a little bit later you get the ECML results. And for each and every possible point in time, you want to know which features are relevant. Before, for the SAGE, what did you do? We masked features and looked at how much is this feature contributing in this context. The problem is we can now not do this for each and everyone because we just have this upper part. But what we can do is, of course, we can do this always for each part and then have a moving average over the SAGE values. And that's exactly what we did. So we proposed to sample at time point t, one of this masking or several of these maskings. We compute the just for these few points, the at some time point, the difference of adding I and not adding it, and then we just take a moving average. One problem remains. We have to have the estimate of what is the revenue if we have the subset of features. So how do we do the estimate for the remaining features? And for that, we have the possibility to, of course, have like a reservoir, which allows us to store an estimate of how the data look like at the moment. We could either store all data, if possible. We could store a representation of the distribution. What we did is we stored an interval with just L. Capital L is a fixed number of data points, and we, in each time step, just randomly substitute these by the new one, which gives us a geometric distribution over the history. And this allows us now to have feature relevance values which, as soon as the underlying model changes significantly, also indicate in how far this features are different ones we should look at. This is an example where we took the Agarwal data set. So it's a data set with a number of just 6 features. We have the ground truth because there are so few features we are capable of actually computing the Shapley values at each interval explicitly. And what we have here, we always have a switch of the underlying concepts where features get, different features get relevant. And you see that these ICNCE, so this incremental SAGE, allows to, this one, allows to follow this pretty quickly. This would be the ground truth, so it approximates the ground truth pretty quickly. And we also compared it to just window-based approaches, where you have to know the size of the windows, which are sometimes a bit delayed, and which is much more costly. And we also use that for the water domain. So here we did autoencoder. And if we have a faulty sensor, then it shows by the different of relevances of features for the autoencoder. Because if a sensor is faulty, it cannot be substituted by others. So you see pretty nicely that these feature relevances incrementally show you what is a faulty sensor. And there's mathematics telling us that this is if it would be static, then it's a valid estimator where we can limit the variance and we can show it's unbiased. It's available as a toolbox, not only ICNCE, but also other methods among those incremental permutation feature importance. Okay, very last topic. Now we can go incremental. Often we have feature interactions. Imagine you have Printen. Imagine you have Schnaps. If you have both together, you have a party. So it's much more. It's a synergy. That's very often the case if you go for example, language models. If I have a sentiment task, I have never forgot this movie all these years and it has remained in my life. This is a positive sentence. If you look at the contribution of single words, never is positive, forgot is negative, this is positive. Never forgot is extremely positive and it's more positive than never. And forgot would be negative, this is really some synergy. Never forgot is something different as compared to never and forgot. How can you compute that? So more or less what you have a team of, for example, having Printen, Schnaps, beer, coffee, and you have to judge how good is this team in each and every possible context. And the context could be various ones. So it might be that, for example, you have a party, you bring everything. Super, it gets better. It might be you have a party where many people have to drive back with a car. Now, the good with a team is you don't need to use the whole team every time. You might say, okay, everyone has to drive back with a car, then I bring Printen and coffee, super. Or you have this one, so you can always bring Printen, but probably not beer with cake. So you have to look at each and every possible subset of your team, how much it's contributing in each and every possible context to have a valid judgment of the value of a team. So first is judgment of subsets of team is what is the S derivative. So for the single Shapley values, we just looked T and T composed with I. Here we look at L, at T and T composed with each and every possible subset of L, and then we have to have this telescopic sum in front of it. And we have to put this in each and every context, so we have to look at each and every possible subset of all possible features not containing the team we want to judge, have this S derivative, and then we have to put in here generalizations of these Shapley coefficients. The problem is with this extension, it's no longer unique. There is this Shapley interaction, there's this and that one, but each and everything is just some term here. And this looks like a nightmare because it's one sum of subsets and this is another sum of subsets. No way to compute that and sample that. So what we did is we rephrased the whole thing and got this big term, which is much nicer because it's just one sum of subsets and a pre-computed term and the revenue, meaning we can do sampling based on this one only. And this is what comes out. I don't go into the details here, so that just show you, okay, this works, because this is for a language model. If we can now judge, okay, Shapley values for one interaction, which would be the original ones. This would be teams. This would be if I want to have teams of 3 partners each. And you see that we compare it to a method which came with the Shapley interactions, which is the blue one. You see, okay, for this one, it's more or less the same. But as soon as we go for teams of 3, the method which came with the Shapley interactions is no longer working, whereas our approximation, depending on how often we sample, is pretty good. So we are capable of judging teams. It works also mathematically. And let me show as a very last thing, it now allows you to not only judge in a sentence for each and every word what it contributes, but also the most prominent teams of 2 or 3 words. You'll love it. It's very positive. Is not bad. It's very is not or not bad. Is very positive. And you can also do that for pictures to show how much parts in the picture contribute as a synergy. So let me conclude. I've been talking about XAI, and I hope it's probably important, it's funny, and we are not yet there. So I've talked about counterfactuals. If you want to use counterfactuals, here's a toolbox. I've talked about incremental explanations, which is ICNCE. There's also this toolbox. And I have talked about how to judge synergy effects, which, for example, would be in the SHAP IQ, which is here, and it was a paper at NeurIPS. And with this, it remains to thank my collaborators. So in this work, it were Andre, Fabian from my group, and people from the kiosk team from Munich and from Honda, and now Victor is in Paris. And also money givers, in particular here, ERC, North Rhine-Westphalian, and DFG. And I want to thank you for your patience. Thank you.
So thank you very much for explaining to us how to make AI less crappy using explainability. Does anyone have any questions for Barbara? Yes, please, front microphone.
Hi, I'm Elisabetta from OneQubit. Thank you for the talk. It was very, very interesting. I have a question about the Shapley factors. How are they different than doing the principal component analysis of the features?
Yeah, so on the one hand, they might be nonlinear, and the principal component is a problem that, also, the principal component, you also would go for independent components, basically. The principal component is, it's completely different. So the principal component would be a linear decomposition, which explains most of the, if you represent in the sense of the least squares representation of the data, whereas the Shapley values tell you how much, so you can use it for each and every possible function. It's nonlinear, so it's telling it you can use it for each and every possible function as a black box mechanism around that. And then it would tell you what one feature is contributing in each and every possible context, taking into account dependent as well as independent, so correlated as well as independent alternatives to explain the output. So it's much more rich, so to speak.
Okay,
thank you. That would be my understanding. So,
I don't know. I was thinking that instead of starting with a set of features that are correlated, with the principal component analysis, you would have less features not correlated, and then each of them you will know which is the way.
But the problem is also it might be that you have correlations. You always explain for an output, so that's one thing. So it's always targeted because the PCA is really a representation thing. And then, of course, PCA and independent component analysis, for example, already gives you much different results. And that would also be a little bit in this area that you might have really correlations which you can compute. You might also have information which you can use alternatively as the output, which is not a correlation necessarily, but it could be another explanation for what you are interested in. And you more or less have a grasp on that. And these are basically the only unique method to do this properly. Therefore, they're at the moment pretty hyped in machine learning. Many love those. Apart from they are very hard to compute.
Okay, thank you.
Thank you.
So I have another question as well, which was a remark you made, more or less a side remark.
Yes.
You said it's very hard to evaluate explainability. And I found that very interesting because coming from more the neuroscience side, this is also a big topic in neuroscience, what constitutes an explanation for us. So I was wondering if this is a similar set of problems or there is particular issues about evaluating explainability for artificial for machine learning approaches that is unique. Could you expand a little bit more on this?
So I would expect the problems are very similar. So there are, on the one hand, purely technical things like an explanation to be faithful, covering everything and whatever. So they are in model explanations, evaluations, which are existing. And I would expect that's more or less the same, that you see, okay, if you restrict to the features, you can still get what you want and stuff like that. The problem is explanations finally are meant to be for people, and people are never without context. So meaning for machine learning people, because for machine learning people, what do you want? You want to have your next NeurIPS paper. Probably. Often you don't care for changing words, so that's as it is, at least if you need your PhD or a position. It's probably not on changing the word, but if you want to change the word, you would need to go to people and evaluate what they can use in their specific context. And that's actually what we are also doing in my group, among others. So we do user studies. And a big problem is that these explanations are often model agnostic. and explanations in practice are never model agnostic, because one explanation, one setting might be good for one person, but not in another setting for another person. And that's a bit of a problem, so how to cover that. And I would expect that you also have this variety in the human brain, that it's not clear how to abstract from the very many factors influencing that. And yeah, for machine learning, people go for user studies for sure, and also for interactions, because an explanation for a person is never A, B, that's it. If you explain to humans, you always have a dialogue, and I think that's the way it is going. And it's particular here, we have this beautiful collaborative research center where there are psychologists, sociologists, and all these people who can do these involved and who try to get a handle on that. And it's super hard, so yeah, we are working on that. Yeah.
Okay, thank you very much. I see no further questions. So thank you once again, Barbara Hammer.